We are now starting AQA A-level year 13 topic in organic chemistry on optical isomerism. We have already studied isomerism in year 12, so now we're just going to move this forward into year 13. In this topic, we are looking at your knowledge of structural formulae and displayed formulae from before, from year 12, and the new material we will be covering is understanding what enantiomers are, understanding how racemic mixtures are formed and why we say they are optically inactive, drawing 3D or 2D structures of organic compounds, and understanding the origin of optical isomerism. So let's move on to our topic. So a bit of recap, sorry. We know there are two types of isomerism, structural and stereoisomerism. And stereoisomers are two types, EZ or cis trans studied in year 12, and in year 13 we will be looking at optical isomerism. So just to recap, then isomers are molecules that have the same molecular formula, but the arrangement of atoms in space is different. And also stereoisomerism is where the structural formula will be the same, spatial arrangement of atoms or 3D arrangement of atoms is different. Let's look at EZ, but2ene. But2ene can be represented by following two forms. Now what is different here then? If we look here, you've got CH3 in the same line. I'm going to draw this. I'm going to call this same line. And you've got two H's in the same line. On the opposite side, you've got the hydrogens diagonally opposite and you've got the methyl groups diagonally opposite. This one we will call Z. So this is your Z but2ene because the methyl groups are on the same in the same plane. And this one we will call E, which is your CH3s are opposite each other. E also means trans and Z also means cis. Now because we have already covered this in year 12, you will need to go back to recap your year 12 knowledge. Let's move to optical isomerism now. Okay, if you look at the top diagram, you've got a carbon that has 1, 2, 3, 4 different groups of atoms attached. We call this carbon chiral, CHIRAL. The mirror image of this, and now what do you notice about the mirror image of this? There isn't much different, is there? You've still got carbon with 4 different groups attached. Okay. However, if we put the two mirror images on top of each other, they will not superimpose. We say they are non-superimposable. So the first rule with optical isomerism is we need a chiral carbon, which means a carbon that has 4 different groups attached. The second rule is the mirror images of the two chiral carbons are non-superimposable. What that means we will look at the next slide. Another good way of doing this is to take your left hand and the right hand and put it as that. So the left hand and the right hand are pretty much mirror images of each other if we spread them out like the diagram. However, if we put one hand on top of the other, then this thumb will move to this side here. So we say they're non-superimposable. Look at this example. This photograph gives you the example of what we mean by non-superimposable. You have to turn the two hands over if you want to superimpose one onto the other. So you have two mirror images which are non-superimposable. Let's move on. So optical isomerism, as I gave you the example, look at your two hands. They are more or less identical. So do this for me then. Take 2 washing up gloves and try putting the left hand washing up glove into your right hand or onto your right hand, and it will not fit. And that's a good example of 2 images which are non-superimposable. So in chemistry, 2 molecules that are mirror images of each other can't be superimposed or optical isomers. But there is another condition here. As I said, the carbon has to have 4 different groups attached to it, otherwise it's not otherwise it's not optical isomer. So let's look at this. Now this is an example of amino acid. So those of you studying biology, you will recognize an amino acid. Amino acid is a organic compound that contains a carboxylic acid group, and this NH2, which we call an amine group. Amine group. So this carbon here, this is the carbon I'm highlighting now. We call this carbon chiral. It's got a hydrogen, a CH3, NH2, COOH attached. It's a chiral carbon. It has a mirror image on the opposite side there, and they're non-superimposable. So the main thing you need to understand here, therefore, is simply the carbon has to have 4 different groups attached to it in order for it to be optically active. Carbon can only form 4 bonds anyway, because it's in group 4, so it's forming 4 bonds. So hopefully that is straightforward. So optical isomers have same physical properties, and the way we test it is we shine plain polarized light through it, and we will look at this later on, and it will rotate light in opposite directions. The practical side of this is normally done in the lab, so when we're in the lab next time, we can have a look at this. Right, moving on then. So here are some examples. Molecule, as I said, just a recap of it, which has 4 different groups attached. We call this chiral carbon. We also call this asymmetric carbon. It's chiral and it's optically active. Optically active means it will rotate plain polarized light either in this direction or in this direction. Okay? Asymmetric means the tetrahedral molecule has no center or plane of axis symmetry. So it does not have a line of symmetry. Moving on. Okay, so let's give you an example. 2-chlorobutane. Now, how is this optically active? Which is your chiral carbon? So the chiral carbon is here. It has a Cl, a H attached, a CH3 attached, and it got a CH2, CH3 attached. So it's a chiral carbon. And there is the 3D arrangement of this. So these are the 3D arrangements which we studied when we did shapes of molecules in year 12. So again, you need to go back to shapes of molecules topic in year 12 to recap on this. The 2 isomers we say are non-superimposable, and they are mirror images of each other, and those mirror images are not identical. They will rotate plane of polarization of polarized light. It's easier to say they will rotate plane of polarized light in opposite direction, clockwise or anti-clockwise. So the name given to the 2 isomers is enantiomers, and here a keyword for you, what we mean by enantiomers. 2 mirror images of the optical isomers are called enantiomers. You don't need to know beyond this for A level. Okay, how do we draw it? Draw the displayed formula first. Identify the chiral center. This is taken from a note which is accompanying these slides. Identify your chiral carbon. Please have a read of this in your own time, and then draw the isomers. Okay, identify the chiral carbon here. So have a close look at this. Which carbon is chiral? So let's have a look. It can't be this chiral because it's got 2 hydrogens attached. Can it be this one? Well, 1, 2, 3, 4. So yes, it can be this chiral. This carbon can be chiral, and this carbon here, this one, can't be chiral. because it has 2 methyls attached. The carbon has to have 4 different groups attached. Okay, so optical isomers are I'm just repeating myself here. Okay, now I want to introduce you to a new term, a racemic mixture or a racemate. So if we have in the chemical process, when we are making these isomers, because we can make these synthetically in the lab, and if the two isomers are in 50-50 proportion, then we will say the two isomers are optically inactive. In other words, they will not rotate plane polarized light in opposite directions, and we call this a racemic mixture or a racemate. So racemate just means the two isomers are in the mixture are in proportion of 50-50, half. So that's just for you need to know. We will revisit optical isomerism when we talk about aldehydes and ketones. Okay, so here just a summary of what I've said. Each enantiomer rotates the plane of polarization of polarized light through a characteristic angle. But because the effect of each isomer cancels each other out, we will say it's optically inactive. Okay. Another example of lactic acid, you can clearly see this carbon which I'm highlighting for you. This is your chiral carbon. It has a hydrogen, OH, CH3 and COOH attached. Therefore, it's your chiral carbon. Okay, and then we put an asterisk to identify the carbon which is chiral. And those are the two mirror images in 3D. Okay, here's another example. Glycine is the only amino acid that does not have a chiral carbon, that does not have an asymmetric carbon there. Okay, that's not asymmetric because it has 2 hydrogens attached. And you can read that yourself as to why glycine is not optically active, whereas alanine, which is another amino acid, is optically active, as we have seen in the previous diagram. Okay, now I am just going to pause it here. You can do this question because the answers are on the slide. Students, I will expect you to do this test in your own time to test your knowledge in order to see if you understand what is going on. Okay, and then again, for my own students, this PowerPoint will be emailed to you, and you can go through this PowerPoint and work through which molecules are optically active. So I'm just very quickly going to go through this, and you need to do this in your own time. And let's just go back slightly. And a key point, then enantiomers have identical chemical and physical properties. The only difference is their effect on plane polarized light. They rotate that in opposite directions. Okay, moving on then into what do we mean by optical activity. Those references are to some textbooks which we normally give in my school. So now let's look at what plane polarized light means. Right, normal light waves vibrate in all directions, as you can see. Plane polarized light is like the lens we have in our sunglasses. All it does is light rotates in one direction. I normally say light just all light rays coming from the sun are just collected into one plane, and they're just vibrating in one direction, up and down, or left and right, rather than hitting you from all directions. So now you can see when when the polarimeter, which measures plane polarized light or measures optical activity, it will rotate light in opposite direction. There's your clockwise rotation there, and then it can rotate light in opposite directions, which is anti-clockwise, as there, anti-clockwise there. Okay, so optical isomers rotate the plane of polarized light. I will not play this video, but there's a link which you can have a look at this. How do polarimeters work? You need a basic understanding of this. Any good textbook will have this. Polarimeters are used to analyze the effect of optical isomers have on plane polarized light. Nicely labeled diagram for you. You need a light source. You need a filter, a polarizing filter, which allows the light in one direction. You need the sample, or light passes through a sample, and then you will measure the plane polarized light in order to which direction it is going into. These terms are not important, so I'm not going to mention these. Uh, all you need to know is if light appears to turn to the right, that's one isomer. If it goes to the left, that's your second isomer. So that's a very quick introduction to what polarimeters are, and these are some of the diagrams you can see on this. Why is this important? Most natural molecules like amino acids or proteins, so on, are chiral along with many other molecules. In nature, only one optical isomer occurs, whereas in synthetically, when we are making different drugs like ibuprofen, we can have two isomers. One has a positive effect, i.e. pain killing or anti-inflammatory effect. The other one can have negative effect or no effect at all. So there was a very famous case, and I will urge you to read about this thalidomide case. And this was a drug to tackle morning sickness in pregnant women. And this was, I believe, in the 1960s. However, at that time, very little knowledge was known about optical activity, and the drug had adverse effects on women and led to deformities in some births. So, what drug companies will do when they see in cases where they have a case where they've made a drug and it's showing optical activity, then in the quality testing they will test those drugs and they will try to make the effective enantiomer. And there are three options which drug companies will use. They can separate the two isomers, and this may be difficult and expensive because optical isomers have similar properties. They can sell the mixture as a drug, but the problem with this is wasteful because half of the drug could be inactive. And the third method, which is used in industry mostly, is design an alternative synthesis of the drug that makes only one required isomer. And the good examples of these are Nurofen and ibuprofen for these. Again, can you see where the chiral carbon is for ibuprofen? It can't be this. It can't be this carbon because it's got two hydrogens there. This carbon here, I'm going back to it, has two CH3s. So if we look at this carbon, it has a CH3, 1. It has COOH2. All of this is the third group, and then there's a hydrogen there, which is the fourth group. So that's your chiral carbon. There's your thalidomide drug. You can have a read of this yourselves. And this is the story which I was talking about in terms of the harms of thalidomide and the benefits of studying optical isomerism. And these are few other examples of different types of drugs which show optical isomerism. And I will end this video here in terms of understanding of optical isomerism. My advice will be on polarimeters. Please have a read of how a polarimeter works. Thank you very much.